Okay, so next is the nucleophilic reactions. So again, we need to see first what the nucleophiles are. So the nucleophile, as the name says, are the nucleophiles, that means nucleus loving, because the nucleus carries the positive charge, so that means they're the positive charge loving. So they're attracted to the positive charges. So by definition, nucleophile is a lone pair donor, that means it's electron rich. And of course, it's attracted to an electron deficient center. And it donates there a lone pair of electron to form a covalent bond. For example, we have here C is a nucleophile which carries a negative charge, and it's attracted to D, which is electron deficient and therefore carries positive charge. By giving its electron to the D, it makes a bond with the D and makes a product CD. Now let's look at some of the examples of the nucleophiles. So the first example is simple anions that can give up a lone pair of electron. For example, oxide ion, chloride ion, fluoride, and hydride ion. Similarly, anionic species containing a lone pair of electron, for example, hydroxide ion, cyanide ion, methyl and sulfate ions. Another type of nucleophiles is the molecules with an extra pair or pairs of electrons. For example, water and ammonia. So if you look at the water molecule, it carries a pair of electrons. Similarly, if you look at ammonia molecule, it carries a pair of electrons. The next type of nucleophiles are the electron-rich pi systems, for example, the benzene, ethylene, and ethine. Okay, so now look at the first type of the nucleophilic reaction, which is called the nucleophilic addition reaction. So we'll talk about the nucleophilic addition reactions of aldehydes and ketones. And we'll look at two examples, reactions with NaBH4, which is a reduction reaction, and reactions with potassium cyanide. So let's start with reactions with NaBH4. So the nucleophile in this case will be the hydride ion. And it's important to understand this hydride ion is basically coming from NaBH4. That's why we need the NaBH4, because it's the source of the nucleophile. Okay, so now let's look at the example. So here we have ethanol, which is an aldehyde. And at the bottom, you can see there's a hydride ion. Because ethanol has a carbonyl group, and the carbonyl group is polarized. So that means the carbon carries partial positive charge and the oxygen carries a partial negative charge. The hydride ion has a pair of electrons. It donates its pair of electron to the carbon and makes a bond with the carbon. So you put a curly arrow from the pair of electron to the carbon. And then you put a curly arrow from the double bond to the oxygen. So in this way, you get the intermediate product. And you can see the hydrogen has made a bond with the carbon. The double bond has broken and oxygen is carrying a pair of electrons and therefore carrying a negative charge. To complete the reaction, we need hydrogen ions. And hydrogen ions can come from two different sources. So the first source is that the hydrogen ions are coming from an acid. If they're coming from an acid, then oxygen will give its pair of electron to the hydrogen and make a bond with the hydrogen. So we put a curly arrow from pair of electron to the hydrogen ion. And the resulting product is ethanol. The other possibility that the hydrogen ion is coming from the water. If it is coming from the water, then the reaction will look like this. We know that the water molecule is polarized, so we put a curly arrow from the pair of electron on the oxygen to the hydrogen of the water. But at the same time, the bond between the hydrogen and oxygen is broken. So we again end up with ethanol, but in addition to ethanol, we get the OH negative ion as well. So overall, as a result of the nucleophilic addition reaction, ethanol, which is an aldehyde, is being converted into ethanol, which is an alcohol. Ketones show nucleophilic addition reactions in the same way. So here's an example of the ketone, and we have a propanone as a ketone. So hydride ion, by donating its electron, makes a bond with the carbon and at the same time break the carbon-oxygen bond. And we get the intermediate product with oxygen carrying negative charge and a pair of electrons. The reaction is completed by addition of hydrogen ions, which can again come from acid or water. If they come from acid, oxygen makes a bond with the hydrogen, and we get 2-propanol at the end, which is an alcohol. If the hydrogen ions come from the water, oxygen makes again bond with the hydrogen, while the bond between the hydrogen and oxygen in water is broken. So the end product is again 2-propanol, but we get OH negative at the end. So overall, a ketone is being converted into alcohol by the nucleophilic addition reaction. Okay, so now look at the nucleophilic addition reactions with potassium cyanide. The nucleophile in this case will be the cyanide ion Cn negative. Again, we have ethanol, which is an aldehyde, but the nucleophile in this case is the cyanide ion, which carries a pair of electrons. So it donates a pair of electrons to the carbon and therefore make a bond with the carbon. But at the same time, the bond between the carbon and oxygen is broken. So put another curly arrow from the double bond to the oxygen, and the intermediate product is something like this, with oxygen carrying a pair of electrons. Again, the reaction is completed using the hydrogen ion. So again, we have the two different possibilities, the hydrogen ion coming from the acid. In this case, we will end up with 2-hydroxynitrile. And if it is coming from water, we again end up with 2-hydroxynitrile, but with OH negative ion as well. Similar is the case for the ketone. So this time we have a propanone, which is a ketone. Cyanide will react again in the same way. We will have the intermediate product, and to complete the reaction, hydrogen will be used either from the acid or the base. In either case, we will get 2-hydroxynitrile. Now we move on to the nucleophilic substitution reactions, and we will look at the nucleophilic substitution reactions of halogenoalkanes. We will look at 3 different examples: nucleophilic substitution by hydroxide ion, the second would be nucleophilic substitution by cyanide ion, and finally nucleophilic substitution by an ammonia molecule. So let's start with the nucleophilic substitution by hydroxide ion. So the nucleophile in this case obviously would be the hydroxide ion. So the general equation will look something like this. So we have this halogenoalkane plus sodium hydroxide, which provide the hydroxyl ion. As a result of this substitution, halogen will be substituted with the hydroxyl ion. So we end up with alcohol. Let's look at the real example. Let's look at the example of bromoethane. So we got CH3CH2Br, while hydroxide ion is as a nucleophile. So we put a curly arrow from the pair of electron to the carbon, which means that hydroxide will make a bond with the carbon, but at the same time will break the bond with the bromine. So we get CH3CH2OH, which is ethanol. And here is the bromide ion that will make a bond with the hydroxide ion, because NaOH gets split up into sodium ion and a hydroxide ion. And that will make NaX or NaBr in this case. An important thing here to remember is that rate of the nucleophilic substitution of halogenoalkanes is inversely proportional to the carbon-halogen bond enthalpy. Here is the table of the carbon-halogen bond enthalpy. You can see that for the carbon-fluorine, the value is highest with 484, while for the carbon-iodine is the least, which is 238. So therefore, CF would be a least reactive, while CI would be the most reactive, because it's much easier to break the bond. It requires much less energy to break the bond in CI compared to CF. Let's move on to the second example, where we have the nucleophilic substitution by a cyanide ion. So the nucleophile here would be the cyanide ion. And here's the general equation. So here we have our halogenoalkane, which react with the potassium cyanide. Potassium cyanide will provide potassium ions plus cyanide ion. And there will be a substitution of the halide ion with the cyanide ion. So we get a nitrile at the end. If you look at the example, we have a bromoethane here, which is attacked by the cyanide ion, carrying its pair of electrons. So the cyanide ion gives the pair of electron to the carbon and make a bond with the carbon, and at the same time breaks the carbon-bromide bond. So the bromide ion is now free. So what we get at the end is the propane nitrile plus bromide ion. That bromide ion will make a bond with the potassium ion to make the potassium bromide in this case. Please be aware that the CN group in inorganic compounds is called the cyanide. For example, KCN is called potassium cyanide, while the CN group in organic compounds is called nitrile. For example, CH3CH2CN is propane nitrile. And our final example is the nucleophilic substitution by an ammonia molecule. So the nucleophile here is the ammonia. It's important to note that ammonia is a neutral nucleophile because it can donate a pair of electrons. So the general reaction would be that when the halogenoalkane reacts with the ammonia, the NH2 is substituted by the halide. So we get nitrile as a product. So the example here is bromoethane plus ammonia, because the nitrogen in the ammonia carries a pair of electrons. So we put a curly arrow from the nitrogen to the carbon, showing that the carbon will make a bond with the nitrogen, and at the same time we put another curly arrow between carbon and bromine, showing that bromine will take a pair of electrons and become Br negative. The important thing to note here is that N is carrying a positive charge because it's making a 4 covalent bond instead of 3. Therefore, the bond between the nitrogen and hydrogen will be broken, so we put a curly arrow to the nitrogen. Another ammonia molecule will donate that pair of electrons to the hydrogen ion and make a bond with the hydrogen, making ammonia. At the same time, it reacts with the bromine as well to make the ammonium bromide. So we end up with ethylamine, which is a primary amine, and ammonium bromide. However, it's very important to understand that in practice, the resulting product is a mixture of primary, secondary, and tertiary amines. So a primary amine is the one in which the nitrogen atom is attached to only 1 carbon, secondary amine where the nitrogen is attached to 2 carbons, and the tertiary amine is where the nitrogen is attached to 3 different carbons. So if you only want the primary but you don't want the secondary and tertiary amines, so we'll have to stop the reaction. To prevent further substitution, concentrated solution of ammonia is used. So we only get the primary amines but not the secondary and tertiary amines. The final type of nucleophilic reactions is the nucleophilic addition-elimination reaction. It's the same reaction where the addition and elimination takes place. So here we're going to talk about the nucleophilic addition-elimination reactions of acyl chlorides. So we start with the first half of the reaction, which is the addition reaction. So we have ethanol chloride, which is an acyl chloride, and water is nucleophile. The oxygen on the water carries a pair of electrons that will be donated to the carbon, so a bond will be formed between the oxygen and carbon. While at the same time, the bond between the carbon and oxygen will be broken. So we put a curly arrow towards oxygen, which means oxygen will take the pair of electrons and become negatively charged. So this is what we get. So that is addition reaction because water has added itself into the molecule. The second half of the reaction is the elimination reaction, in which the chlorine and hydrogen will be eliminated. So chlorine takes the pair of electrons and then separates itself from the molecule, but at the same time the pair of electrons on the oxygen is used to make again the double bond between carbon and oxygen. So we get a double bond between carbon and oxygen. Chlorine has removed itself as a chloride ion, while the rest of the molecule is still the same. In the next step, the chloride ion will donate its pair of electrons to the hydrogen and make a bond with the hydrogen, making HCl. And the rest of the molecule is CH3COOH, which is this. In the exam, you will have to just write the one-step reaction, which looks something like this. So you start with the addition reaction, which is this. And then you start with the elimination reaction, which is this. And then you end up with the final products, which is this. Let's have a look at another example. So again, we have ethanol chloride, but this time our nucleophile is ethanol. So the rest of the reaction mechanism will be the same. So the oxygen carrying a pair of electrons will make a bond with the carbon. Chlorine is removed here, the hydrogen is removed here, and then chlorine and hydrogen combine to make HCl, while the double bond between carbon and oxygen is restored again. So this is what we get at the end. Another example is the reaction of ethanol chloride with ammonia. Again, we put a curly arrow for a pair of electrons from the ammonia to the carbon, and then from double bond to oxygen, breaking the double bond. Chlorine is broken, hydrogen is broken, make double bond between the carbon and oxygen is restored, and this is what we get at the end. And the final example is between ethanol chloride and methylamine, in which case nitrogen provides the lone pair of electrons, and the rest of the reaction is the same. If you have any question, please write in the comment section, and if you like this video, please don't forget to subscribe, share and like. Thank you very much.